Hello and welcome to AI4. Our next session is going to be led by AMEEN KAZEROUNI. He is the head of AI and ML research at Zappos. Please join me in welcoming AMEEN to the virtual stage. All right, take it away.
Thank you for the introduction. Just gonna get my slides ready. All right, so you will often hear Zappos referred to as a service company that happens to sell blank. It could be shoes, accessories, clothing, and experience. And that is exactly what my team at Zappos is tasked with doing, increasing operational efficiencies and driving an elevated customer experience using artificial intelligence and machine learning driven experiences. My name is AMEEN KAZEROUNI. I'm the head of the ML and AI research and platforms here at the Zappos family of companies. And today we're going to be talking about the role of platforms and process in realizing a tangible ROI on your AI and ML investments. So what does machine intelligence at Zappos, which is the name of the organization, do? Well, it covers a variety of different areas, various different ecosystems, starting with the search ranking algorithm for our search relevance, an experimentation platform that allows for testing the efficacy of various features and experiences that we want to push out to the website, profit intelligence, which is effectively a statistical and mathematical understanding of the unit economics of each item that leaves our warehouse. This could be models to predict likely damage rate, return rate, ship costs, etc. We have supply chain, which is price elasticity to demand forecasting to help with inventory management. And of course, our personalization strategy, which is effectively a cohesive personalization experience ranging from various widgets you see on the site right to a one-to-one personalized search relevancy algorithm. So while catering to this wide gamut of experiences and internal and external clients, there's two possibilities. You either end up with redundant and repeated development efforts, or we can focus on a robust and reusable platform with delivery-oriented processes. So today we're going to talk about that platform and that process, and then use a case study to walk through it and see how it all ties in together. So first, let's just do a high-level understanding of the component architecture of the machine intelligence platform. We have an event ingestion framework that is focused effectively on acquiring data and making data available to the machine learning organization. We then have a DAG Orchestrator, which is effectively a framework that allows us to do stuff with that data. We then have a well-governed feature space that is catered to by our feature library. And finally, a Microservice API that acts as our inference layer. So let's talk about the event ingestion framework. The event ingestion framework is what we call engineer driven. What I mean by that is whether it's our backend engineers, our front-end engineers, mobile developers, doesn't matter. Each one of them are able to maintain a collection of protocol buffers that represent the events of interest to them. These protocol buffers can be registered by an engineer at any time, which then in turn triggers a build process that modifies the event ingestion framework to be ready to receive that data. There's two primary benefits here. One, the engineering team has no dependence on the ML platform team to register new data types, and there's no development cycle required for that process. Two, the events are largely self-documenting. Protocol buffers are reasonably readable, and since the events are structured specific to each event that the engineer hopes to capture and not try to jam into a standardized format, it's extremely self-documenting, very readable, and easily accessible to other engineers. We additionally make a lightweight client-side event emission library available to the engineers. This event emission library is written in Java, Swift, JavaScript. It effectively allows for the engineers to be able to emit these events without worrying about the overhead of bundling events together, sessionizing the events to make sure that the session ID is standardized across events coming from the same session. It handles that overhead and allows events to be fired from the mobile apps, from backend systems, from the website, wherever. An interesting artifact about this experience is that Server-side events maintain a client-side context. So when a client requests data from the server, it also lets the server know the client-side context, which the server should then fire to this event ingestion framework while firing server-side events. Another critical aspect of the framework is what we call multi-destination support. What this means is we've decoupled the system of receiving data from the framework that emits the data to various storage layers. So the receiving API can be firing these events to Kinesis for real-time analysis, can be firing this to Redshift for data warehousing, S3 for long-term storage, or ingestion into frameworks like EMR. Lastly, the entire framework is self-serve, right from the event definition to the routing layer where you define where you want each event to go for different teams. This event ingestion framework and its self-serve nature has resulted in a 60 to 70% year-over-year increase in event generation and new event type creation. This shows us a tremendous amount of adoption and a sense of ownership that each engineer feels towards events that they've created themselves. And it results in an extremely rich and dense data set for the machine learning experiences. Next, we have our DAG Orchestrator. The DAG Orchestrator is probably the most important build or buy decision that you will face while designing and developing your machine learning platform. Kubeflow, MLflow, Airflow, all the flows are just an example and testament to the fact that this is a critical component of the ML platform, and it is difficult to solve for. As you can see, there's a lot of people trying to solve for it with different technologies. Zappos itself went with the build approach. We effectively developed a orchestrator that allows us to execute a series of steps performed in a particular sequence. This could be data set retrieval, model training, validation, deployment, to production environments, or routing insights back into the data warehouse to be analyzed in conjunction with other data. So a workflow can complete, deploy a model to production, or trigger other workflows to generate reports, to train new models, etc. One of the most important takeaways while developing this system and while researching whether we wanted to buy a solution here was the importance of your DAG orchestrator being extremely well connected. What I mean by well connected is that each component inside your orchestrator should be able to connect to a multitude of different storage layers and various data sources in whatever cloud computing framework you are leveraging at your organization. The importance of this is that you do not need to move data around just to be able to access it inside your orchestrator. Secondly, same principle, you want to be able to leverage all the different types of compute resources that are available at your disposal, whether it's cookie cutter or bespoke auto ML solutions, whether it's EMR, whether it's EC2, ECS, whatever your compute resource that you're dependent on, you want your orchestrator to be able to deploy jobs to those various frameworks so that you're not limited to choosing compute and storage layers based off what the orchestrator supports. What this means is you want something that is flexible and extensible. You want an orchestrator that is onboarding with new services at a regular cadence. And if you're building it in-house, you want to make it modular enough to where you can quickly onboard new services as your engineering community starts using them. Lastly, governance and access control can prove to be extremely critical when it comes to this orchestrator because it is an engineering layer that has got access to a lot of data and a lot of computational resources, which can get pretty expensive. Now, this is an extremely nuanced layer of your ML platform, and I would strongly recommend researching the buy option before trying to build this in-house. Next, we have the feature library. A feature library, fancy as it sounds, comes down to a very simple concept, which is the feature space that you use for the various machine learning algorithms that you're building in your organization requires a couple of things. You want good governance, which means that features that you develop and derive one way should be derived the same way across multiple models, but also in training phases and inference phases, which may be dealt with by different teams. Two, you want your feature space to be reusable. Feature generation can become an extremely expensive step in the machine learning process, and having a library of features available for your ML scientists to peruse can result in a higher velocity ML lifecycle. Now, you don't need to start with a complex engineering solution here. It's very reasonable to start simple. At Zappos, our quote unquote feature library and our feature governance process was a simple code review process with version controlled SQL queries. This provided a library of queries for our machine learning scientists to search through. Structured naming convention made features easy to find. And more importantly, the version control SQL process allowed us to confidently update feature derivation, feature queries to stay up to date with event definitions while being assured that downstream processes would be using the same feature. This process evolved into a platform. Today at Zappos, the feature library is an API that allows you to create feature groups and retrieve features for varying timeframes for training and in real time for inference. Lastly, we have our microservice API. This acts as our inference layer. There's nothing machine learning about it, and that's how it should be, in my opinion. A microservice API that allows us to expose our machine learning models with all the layers of scaling and redundancies in place that any tier 1 API would have. The microservice API lends to fault isolation and staggered deployments, which reduces the blast radius of errors that may be pushed into production. From a machine learning perspective, talking about the auto-scaling a little bit, it's got EC2 instances running in auto-scaling groups, a Redis cache that is shared across the microservice with auto-scaling enabled for some pretty aggressive caching for predictions that have been already made, backed by a Dynamo instance for batch predictions. A batch prediction effectively is, it's our preference at Zappos to pre-compute predictions when possible and pre-deploy the output, the inference of various machine learning models so that the API is only exposing quick Dynamo lookups when possible. The benefit of this is that doing live inference with various classifiers can actually get a little laborious and technically difficult to deploy into a production environment. When we do require real-time inference, we rely on SageMaker endpoints, where our machine learning scientists are able to deploy model artifacts in a language of their choosing, and the microservice API layer merely proxies those. So a last component of our microservice API is standardized resolvers. This is something that's unique to this particular ML API. For example, lemmatization for models that are term-based. A lot of our search algorithm ML models require lemmatization of the term before we send it to a particular model in the backend. And we want to make sure that that lemmatization is the same, whether it's during training, inference, whether you're hitting the search engine. So we have a standardized resolver for that lemmatization. A more complex example would be synthetic twins. If a model is a customer-based model, but we're not able to make a prediction for that customer, you can hit the feature library, get a vector back for the customer, and then look up in a synthetic twin engine, which is a separate model, who similar customers are, and try and serve a blend of models for them. This is a relatively complex process that you do not want to keep recreating every time you have a customer-based model. So it's a standardized resolver that's available inside our API. So those are the various components of the component architecture. So let's talk a little bit about process. The process are broken up into 4 key components. And if you see, I've kind of focused on problem formulation and data set design more than the actual model development. This is because I believe that these 2 steps can make or break the machine learning process. So let's start with problem formulation. Problem formulation is effectively translating the business problem into a mathematical one. What this means is you take your business stakeholders' requirements and represent it as something that can be solved with a machine learning problem. Secondly, you have data set design. It is absolutely critical to be deliberate and modular with your feature selection. A complex data set chosen upfront can result in extremely expensive computational clocks and in a model that doesn't produce exactly what you were looking for. Once you've nailed these 2 steps, you move into the actual model development. This is your standard model selection, training, and validation process. And finally, we have model deployment, which is the production deployment and testing of the machine learning model and experience that you're planning on serving. So now that we've got the platforms and the process that we use at Zappos, let's pick a case study, an actual business problem that we solved for using machine learning, leveraging this platform, leveraging these processes, and realize a tangible ROI and walk through how it all fits in together. So let's discuss this case study. The problem we were faced with was a high return rate. So let's talk about what returns means to an e-retailer. Primarily, it builds customer trust. In e-retail, when you're shopping for clothing and shoes, you're concerned about how it looks, how it falls, how it fits. And there's comfort in knowing that you can send it back free of cost. You can send it back with an advanced exchange and receive a replacement item with next day shipping. Now, what does that mean for the retailer? It's improved customer trust, it's improved customer relationship. It's that wow factor that Zappos strives for, but it's also a strain on the bottom line. But it's become table stakes in retail today. Having free returns and easy returns is almost a requirement to be an online retailer. But you run the risk of damaged inventory coming back. You have increasing shipping costs, and sometimes it may not be a value prop. Very often, the Zappos customer is buying an assortment of products, selecting between them, and sending back the ones they don't need. But sometimes, maybe the customer is just dealing with a bad experience. And let's dig into that a little bit. Let's talk about the problem formulation. We were asked as the machine intelligence organization to help with the return rate being too high. We launched an analytical study, and we realized there was a disproportionately high sizing related return rate. Now, what a sizing related return rate is, effectively customers buying the same item in multiple sizes, returning one and keeping the one that fit, or worse, buying something, realizing it did not fit, having to return it, buy a replacement product, and sometimes as many as 3 times is back and forth before you get the right item. Now, that is objectively a negative customer experience. It is not ideal. It is leveraging a value prop, but it can be easily avoided. So we found ourselves in a lose-lose situation. Now, what's cool about a lose-lose situation is we see it as a win-win opportunity, which is where we identified where we could use machine learning. If we could build a model that predicted the customer's size in every shoe that we sold, such that they bought the right item the first time, we could solve for this, which brings us to class label selection. Now, if we went with the definition of the problem that I stated earlier, our class labels would be every possible size, every half US size, European sizes, Australian sizes, alpha sizes, you name it. Very quickly, you realize that this is quite the massive multi-class classifier. So we went back to the drawing board. What exactly are we trying to predict? Further analysis showed that most sizing related returns happen within 3 half sizes of the customer's usual size. So this was interesting because it allowed us to restate this massive multi-class problem as a simple binary one, round up or round down. And now we had an opportunity on our hands, a relatively simple classifier at a problem that the business really needed a solution for. So problem formulation, check. Next, we have data set design. We have our event ingestion framework. We've got an extremely rich collection of events about customer behavioral data. And we've also got a very rich collection of events about how each product is being interacted with. So we could have started with a large and complex data set that we built and derived to start building a massive model. But we also had purchase data available to us. And this is where being deliberate about the feature space comes into play. Purchase data, order and return data is available at runtime. It allows us to leverage our feature library to easily access this data. And it gives us an opportunity to start simple. So we decided to build a very simple model, leveraging the purchase data to better understand how much information was actually packed in there. And we realized that we were able to build and deploy a model just using that information. Furthermore, once we deployed the initial model, we realized that we had a gap in our data. So we created a feedback loop. What that feedback loop was sending out a survey to customers asking how did it fit? Was it too big? Was it too small? Or did it fit just right? This data became a very valuable piece of information for us to feedback loop into this model and make the model even more accurate over time. Next, we have model development. I'm going to reiterate the importance of keeping it simple. We started off, as I described earlier, by restating the problem to be an easier one. We went from a multi-class classifier to a simple binary classifier. We actually then took this even a step further and decided to build a collaborative filter. The reason we did this was because we found that it was hard to deploy classifiers to make real-time inference in production, but a collaborative filter would have been easier to deploy, which led us to a new problem. Pre-computing all these predictions would require us to have predictions for millions of customers and hundreds of thousands of products. So we were now faced with this conundrum of live inference being hard and batch inference being too massive to deploy. And that is where one of the cornerstones of our ML framework emerged, which is ensemble deployments. Break down the problem. We derive two pieces of information here. One being the customer baseline, the size that they usually shop in, and two being the product bias, the usual deviation from a baseline that a product experiences. We used our DAG orchestrator, keeping inference in mind, to deploy these two components behind two microservice APIs, and we were able to ping them both depending on who the customer was and what product they were looking at to make a prediction at runtime. Lastly, I want to iterate that tuning is critical. A nicely chosen set of hyperparameters can result in drastic impact on your model accuracy. Zappos has gone with a buy solution where we leverage a third-party piece of technology to track every hyperparameter, the commit hash of the code base at the time of training, the commit hash of the query to know the data that was reused, and the accuracy of the model with that hyperparameter set. What this results in is a reproducible model at all times. And that is critical because the cost of losing a good hyperparameter set can prove to be very emotionally strenuous if you've experienced it. Now we have deployment. Let's talk about phase one, which was the simple collaborative filter, a two-part deployment with the baselines and biases, a microservice API, and a contract that we committed to. So our downstream services knew what to expect from the model. This sizing algorithm today is a collection of neural networks running in production, doing live inference, proxying SageMaker endpoints, which makes it language agnostic. As we discussed earlier, our machine learning scientists can deploy these model artifacts in Python, and our API can expose it in Java, and uses about 700 to 800 different features from the feature library in real time. But if you notice, we started very simple. 2 features, batch deployment, collaborative filter, followed by neural networks, 800 features, live inference. But start simple and evolve up. Lastly, we have testing. Define accuracy with the original problem in mind. This is critical. The business problem at hand here was a high return rate. So the accuracy of the model doesn't matter if we can't actually bring that return rate down. So what we've learned early on is reality when possible, but proxy when needed. What that means is just because the model was optimized to predict the size of a customer in a shoe to be the size that they keep when they buy that shoe doesn't mean that it's actually going to make them buy that size in production. So we dark launched the algorithm to see exactly what predictions we were making and what the customers were doing. Were we actually changing their minds? Were they actually buying the size we recommended? And how much incremental change in behavior were we causing? And that is what we A/B tested. And that was our success criteria, not the accuracy of the model. Upon A/B testing this, what we did was for 50% of the customers, we released the sizing experience. We made predictions for them when available. For the other 50% of the customers, we clocked the prediction we would have made, but let them go about their shopping experience without interfering. We ran this experiment for 2 weeks. Over the course of those 2 weeks, we collected data and looked at the orders going out. We then waited 4 to 5 days for the returns to come back to see exactly how many items were returned, how many items were kept. And we saw that this little sizing experiment of ours resulted in a 10% reduction in the sizing related return rate with the 2 features, with the collaborative filter, with the version control query for our feature library. We doubled down on the investment. We invested in that platform. We built out the feature library. We built out live inference. And today, the multitude of neural networks with the hundreds of features predicting sizes for customers in production over the last 2 to 3 years has reduced the sizing related return rate by over 30%. And that's a tangible ROI, and that's millions to the bottom line. So hopefully this presentation has shown you how robust platforms and clean processes can really give you a good return on your AI and ML investments. At this point, I'm happy to take questions, and I hope this presentation was informative for you.
Awesome. Thank you so much for that insightful presentation. We all really enjoyed it. I hear a big virtual round of applause from the audience. All right, if you are looking for your next session, you can check the program page or take some time to do some virtual networking and connect with your peers. Thank you so much, and we'll see you around.